Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, dear students. Welcome back to this TV Learning Series program. I'm teacher Patrick, and I will be with you in chemistry for senior 3. And we're still looking at the unit 5, which is the rate of reactions. Remember, this is lesson number 3 of, remember the previous lessons. We looked at the first lesson was measuring the rates of the reactions and looked at different methods. And the second one, we looked at the effect of the concentration on the rate of the reaction using the experiment that we talked about, that we did together. The demonstration, I hope you still remember that. So this is lesson number 3. We are still talking about the effect of other factors, because we had even mentioned these other factors, you remember them? So these are some of them. We look at the effect of temperature, we look at pressure, catalyst, and on the rates of the reactions. So those are probably, if time allows, we'll be able to also look at the effect of the effect on the rate of the reaction when we are increasing the surface area of the reacting particles. So by the end of this, or by the end of this lesson, we'll be able to look at I hope you'll be able to explain the effect of temperature, as we have said, pressure, surface area to volume ratio, the catalyst, on the rate of the reactions. I hope you still remember about the effect of concentration. If you remember what we talked about, the concentration, we said that if you increase the concentration, the rate of the reaction also increases. Concentration, what do we mean by the concentration? We're just trying to maybe to go back and think about the concentration that we did. So when you look at the concept, we are talking about how much of the solute is in the solvent. How much of the solute is in the solvent. And how much of the solute is dissolved in the solvent can also increase the rate of the reaction, and that is the concentration. Said if the concentration is high, we expect a lot of collisions. Colliding molecules are also high, and as I said earlier, reactions take place by chance. And the chances can be increased or can be reduced by the factors that we looked at. So when you increase the concentration, that is what we talked about in the previous lesson, that when the concentration increases, the rate of reaction increases as well. So we said they are directly proportional. So there is a direct proportionality of the rate of the reaction and the concentration. So meaning if we decrease the concentration, that is vice versa. If the concentration is decreased, then we expect a decrease in the rate of the reaction. Let me just take you briefly in the previous experiment that we did. You remember we were reacting sodium thiosulfate with hydrochloric acid. And we said this reaction produces sulfur, which is produced in solid form as cloudy, white, cloudy, yellow precipitate, which is formed. We said when it is formed, then we are determining the speed at which that cloudy, yellow precipitate forms. We have said it is a clock reaction because we are using the clock that we are timing the speed of that reaction. Remember, we started with 50 reacting with hydrochloric acid. The 50 cubic centimeters of the thiosulfate ions were reacted with the 10 cubic centimeters of hydrochloric acid. And that was the first part of the experiment. In the second experiment, we had reduced this one to 40 cubic centimeters of the sodium thiosulfate. And this one still reacted. I said the concentration of the acid is kept constant, does not change. That means the volume of the acid does not change. You remember before we added hydrochloric acid, we added 10 cubic centimeters of water. So that means we are diluting this solution. The solution was diluted. And then we reacted the whole of this one with 10 cubic centimeters of hydrochloric acid. So the reaction is repeated, keeping the volume of the sodium thiosulfate the same. You don't change it. And then this reaction takes longer time. Why? We had decreased the concentration. So that means the reacting particles, the thiosulfate ions which are here, are not the same as the thiosulfate ions in this solution. Because adding water dilutes the ions. So that means this is a dilute solution. So we expect this reaction, as we did, took a longer time as expected compared to this one. So in the next experiment, you are supposed to measure 30 cubic centimeters of sodium thiosulfate. And this time, you mix it with, now this is 20 cubic centimeters of water. And then you mix it with 10 cubic centimeters of hydrochloric acid for the reaction to take place and the precipitate. This one will take much longer time compared to this. So the concentration, increase in concentration, increases the speed of the reaction, and the decrease also decreases the rate of the reaction. So that was what we talked about in the previous experiment and in the previous lesson. So this time, we are just going to look at other factors. But before we look at other factors, I would also like to just make a reminder of what happens. As I said earlier, reactions take place by chance. When they are colliding, the molecules are moving, they are moving in random motion. So by chance, when the molecules happen to meet each other, then the reaction takes place. Sometimes they meet and the reaction doesn't take place. So what does that mean? We explain that using the collision theory. Here, for a chemical reaction to happen, any chemical reaction, think of any chemical reaction. Reactant particles must collide with one another. So because particles are in random motion, and then they collide by chance. The particles must have enough energy for them to react. As I said, they may come together, but not react. They bounce off each other. So they have to collide with a certain amount of energy. That is when that collision is called a successful collision. A collision that causes the reaction to take place is called a successful collision. As I've said, particles must have energy, enough energy for a successful collision to take place and for the reaction to occur. This amount of energy that causes successful reaction, that causes successful collision, we call it activation energy. Energy, the minimum amount of energy needed by particles for a collision to be successful. So this particle has to collide with that one. Even that one has to collide with that. But for the reaction to take place, the collision has to be successful. And it is successful only and only if those colliding particles have enough energy. So we can look at something else about still looking at the successful collisions are still the same as useful collisions. So at low temperatures, talking about the useful collisions, at low temperatures, most particles will collide with each other, but most of them may not have. So when you increase the temperature, probably we can go to the next slide and look at the effect of the temperature. How does the temperature affect the speed of this reaction? The greater the rate or the frequency of successful collision, the number of times the successful collisions are taking place, the greater the rate of the reaction. If the temperature of the reaction mixture is increased, what do you expect? The reactant particles move more quickly. They regain the kinetic energy. They move very fast within the solution. And as that energy increases the chance, that movement increases the chance of colliding. If they are moving at a higher energy, at high speed, then the collision is likely to take place. The energy of the particles increases, that is the kinetic energy of the moving particles, as a result of increase in temperature. The frequency of successful collisions between reactant particles also increases. How many times do these particles have to meet each other? That's what we call the frequency successful collisions. Remember, we have said successful collisions result into a chemical reaction. The proportion of collisions which are successful also increases the rate of the reaction. The proportion, that is the number. As the energy of the colliding particles increases, the frequency of successful collisions increases as a result of increase in the kinetic energy or the moving particles. Explain what is meant by, we have talked about the successful collision. That is a very important term that you shouldn't forget, successful collision. A collision between reactant particles with enough energy. Take note of that, with enough energy. That energy is the activation energy or more to produce a reaction. So for the reaction to take place, there must be a successful collision. The effect of temperature on the rate of reaction is due to the two factors. Those two factors, you have frequency of collisions and the energy of collision. Those are two important points to remember when we are talking about the effect of temperature. Frequency of collisions and the energy of collisions. So that energy of collisions, we have said, is the activation energy. So we said for the successful collision to occur, those colliding particles must have enough amount of energy. That is the activation energy. Those two of them increase the increase in energy is usually the more important factor. So the rate, these are two reactions now compared. Assuming those reactions, as we have said, some reactions, not necessarily this. We may have, we usually use this reaction, calcium carbonate reacting with hydrochloric acid to produce the calcium chloride, which is aqueous, plus water, plus carbon dioxide gas. That is the amount of the gas is being produced. So now we are comparing two reactions occurring at different temperatures. So those two reactions occurring at different temperatures, either one is higher than the other or one is lower than the other. So we have the volume of gas produced on this graph and the time from the start of the reaction. So when you look at this graph in green, that is the sketch, that curve is showing that the reaction is taking place at low temperature. And this one in red, it is taking place at high temperature. And it is more steep. So it occurs, actually it reaches the end point before the one with the lower temperature. Because when you look at these are the two, there are two reactions, similar reactions. Take note of that. They are similar reactions, but they are occurring at different rates, occurring at different temperatures, I beg your pardon. Different temperatures. So the time these reactions come to the end will not be definitely not the same. This is shown by these two curves. When the results are analyzed, you'll find that the reaction at lower temperature will take longer to reach the compression compared to the one with higher temperature. That is the one in red. So that is what happens with the rate of the reactions. We have another factor. You remember we had mentioned some of these factors. Another one is effect of pressure on the rate of reaction. Pressure. When we're talking about pressure only deals with gaseous molecules. So when we talk about the pressure, think of the reactions that contain gaseous molecules. The reacting particles are in gaseous form. Why are we talking about only pressure? Remember, solids and liquids are incompressible. So they are not affected by pressure. So if they cannot be compressed, then it means they have no effect on pressure. So gases, because the particles are all spread or they are far from each other. Look at this. These are particles of the gaseous molecules. Now, when you apply the pressure on these gaseous molecules, that means you compress them. You compress them. What happens here? So you increase the pressure on these gaseous molecules. What happens? These gaseous molecules tend to come together. They tend to come together, close to each other. What does that mean? That when they come close to each other, there are high chances of these particles colliding with each other. So these particles here, because they are sparsely or they are not close to each other, the chances of colliding, this coming together with this in a random motion, is limited. But for these ones which are very close to each other, the chances are increased, meaning that when you increase the pressure, what happens? You increase the chances of collision, and that is successful collisions. That means the reaction takes place faster. This is similar to concentration. It is similar to the concentration. When you reduce the pressure, then what happens? You are reducing the chances of collisions with those particles with enough energy to come together. So you are reducing that chance, meaning you reduce the rate of the reaction. So increase in pressure increases the rate of the reaction. Changing the pressure only affects the reactions with at least one gaseous reactant. Because I said other substances cannot be affected by pressure. They are incompressible. Increasing the pressure causes the reactant particles to be closer. That is what I was just explaining. They collide with each other more often and hence increases the rate of the reaction. I think that makes sense. If you consider it with, even comparing it with the concentration, it is pressure is also directly proportional to the rate of the reaction. So let's look at the effect of the catalyst. Catalysts we have seen catalysts. Many catalysts are used in the reactions. And at least you remember, at least by now, as a senior 3, I think you should be knowing what a catalyst is and what it does. Catalysts usually speed up the rate of the reaction, increases the speed. Increase the rate of the reaction, but do not alter the products of the reaction. And change the chemical in mass at the end of the reaction. These are some of the characteristics of the catalyst. Only a very small mass of catalyst is needed to increase the rate of the reaction. You don't need a lot of mass for the catalysts. They work in small quantities. However, not all reactions have suitable catalysts. There are some reactions that cannot be easily catalyzed. Different substances catalyze different reactions. We have seen this one. When you go to unit nitrogen and its inorganic compounds, we look at the Haber process. You have met this one. Sulfur and its inorganic, that is unit 3. So you look at the contact process. We have seen that one. If you remember the decomposition of hydrogen peroxide in the production, in the preparation of oxygen gas, those are some of the reactions that are catalyzed. Those are some of the reactions with with their catalysts. How do the catalysts work? That is what we are just going to see. How do these catalysts work? That is the question. And how do they increase the speed of the reaction? That is the question each of us should be asking ourselves. And then at the end of the day, we'll get to know how. Catalysts allow an alternative reaction pathway that has lower activation energy than uncatalyzed reaction. So catalysts creates creates a shortcut. If you are moving from one place to another, you're going to visit your friend, usually you prefer, as long as you have program, you prefer to use a shortcut, not use a long cut. Use a shortcut that can easily take you to where you want, as long as it doesn't change anything. However, it does not increase the frequency of successful collisions, because greater proportion of collisions has the activation energy or more. The effect of catalysts on the activation energy can be analyzed on this graph. I just want you to look at this graph properly. Look at this. This is a reaction profile for a certain reaction. It is showing the reactants here and the products produced here. So this is the amount, this is the activation energy. That is for every reaction. Each reaction has got its activation energy. That's why reactions occur at different rates. At the beginning, we said there are some reactions that take place slowly, others are very fast, others are instantaneous, you can mention. So you see, this is an alternative route. This alternative route has got a lower activation energy. That means if the activation energy, for the reaction to come here, it has to pass through all this hill. This is very steep. So if that hill is lowered, that is the amount of energy. If it is lowered, it means it will turn into the products with ease. And that makes sense. Lower activation energy using a catalyst. So this is an alternative route where the catalyst has been used by changing. This is some of the examples. You are familiar with the enzymes. They are catalysts in nature, and that's how they work. They provide an alternative route to another reaction. So we can also look at the rates of reaction, surface area to volume ratio. So you are given lumps. Those are big chunks. Maybe you have these like pieces of chalk. The chalk is mainly calcium carbonate, and you have these, it could be lumps like this one, or it could be in powder form. For a given mass of solid, large lumps have smaller surface area to volume ratios than smaller lumps or powders. If a large lump is divided or ground into a powder, its total volume remains the same. The area of exposed surface increases. The surface area to volume ratio increases. So if I break this one into the powder form, or if I make the powder out of this, what does that mean? It means that I'm exposing every particle that is here to another substance. But if it is in this form, large chunks, it means that the particles on the surface will be able to come into contact with another reactant. So large chunks of this, of the acid, large chunks of this one will reduce the reaction rate. So this is what lumps versus, the greater the rate of frequency of collisions, the greater the rate of the reaction. If the surface area to volume ratio, a reacting solid is increased, more reactant particles are exposed. That's what I've talked about. The frequency of successful collisions, I've also talked about it. Then the rate of the reaction also increases because of the successful collision. So we can also mention something like this. I've just given an example here where you have, this is small, so they are in different sizes. So meaning this is surface area, volume. So the smaller one, you'll see it has a larger surface area compared to a bigger one. This is surface area to volume ratio. This is 2:1. This is very big. This is 6:1. So the surface area to volume ratio is bigger here. Increase in surface area of the solid, the rate of the reaction will be increased, as we have mentioned. That is what we have talked about. This is greater surface area. The reaction occurs very fast, and this is lower surface area. The gradient of the line equals to the rate. It is faster here. So this is greater surface area, which is in powder form, and this one will be in lumps, in lump form, or in large chunks. So I thank you so much for listening, and I hope we've been together. Next time, we'll have to have some questions and we'll revise together. We are left with Onre, and I just want to give it to you as an assignment. Look for where you can get the information. No, but we actually have your REB platform, e-platform. Just get some books there, read, and find out where you, the light affects the rate of the reaction. I hope we'll meet again in the next lesson. See you. Bye-bye.